All right, guys, welcome to the first video in rotational motion. So in this chapter, we are going to switch from translational, which we know is linear, to rotational. And the word we're going to use for rotational, when we find values for rotational, the synonym for this is going to be angular, because we're moving through degrees or angles. So what we want to do is we want to look at a simulation that shows how the linear and the rotational are connected. So let's go ahead and I'm going to go to that sim, share my screen. And minimize that. So we have a wheel here, and it has a radius of 0.2 meters. See the spokes are in colors. And so what we can do is we can look at how far the wheel travels given a certain amount of rotation. Now, the units of rotation you're most familiar with are degrees, and hopefully you know that one revolution of a circle is 360 degrees. So we're going to speak about it in terms like that until we get to the official unit. So let's let this wheel go through one revolution. I'm going to go ahead and hit start. We'll see if I can stop it right when the red spoke comes back to where it started from. Okay, so here we have the red spoke. We went through one revolution, and we can see that in centimeters, we went through 125 centimeters, or 1.25 meters. And that is for a particle on the outside. Now, what do you think is going to happen if I shrink this down to, like, what if we were looking at the particle that was halfway between the center and the edge? So if it had a 1/2 radius, what do you think we're going to see on this ruler if I shrink that down? Well, make your prediction while I reset. Okay, and let's start, and we'll go through one revolution or 360 degrees. Whoops, shoot, wrong button. Okay, and we went through 63. So we went about half. So half the radius gave us half of the distance. So what we see right away is that when we're talking about rotational motion, we have both the values. We have a linear value, so this wheel traveled in a linear fashion, but it also rotated. Now, did the 2 points on the spoke at the R and 1/2 R have different angular values? No, they both went through 360 degrees, but linearly, the smaller radius gave us a shorter distance. So let me stop sharing my screen here, and we'll go back to our note page. I'm going to hit focus. I feel like I'm a little blurry this morning. And what we're going to see is that, so we know that linear distance is, the unit is x. And what we're going to see is that angular has a unit of theta. So we see that our, if you think about the fact that as the radius went up, the distance went up, it's going to give us an equation that looks like this. And so linear distance equals the radius times theta. And so this ties together, it's our first equation that ties together linear and angular. And while this is going to vary for every point on the spoke, what we see is for angular values, all points, so if I have a circle here, and I've got a radius, if I have a point here, or here, or here, those are all going to have, all points along a radius have the same angular value, have the same angular values. Why? Because they carve out the same number of degrees. And what we're going to see in a second is we really want to talk about radians. But the linear distance they travel depends on the radius. So if you take that angular displacement, so, you know, if I had like 10 degrees, we're going to convert that to radians, and I multiply that by the radius, it's going to give me the linear distance. Now, you'll notice that you're probably familiar with theta, but we have to have a way to differentiate between linear and angular values. And so what we do is we switch from the our alphabet. So here's linear and here's angular to the Greek alphabet. So we have X here, and this is going to be theta. We also have velocity and acceleration that we want to talk about. Now, the lowercase Greek letter for A is alpha. So the symbol looks like a fish with its front cut off. And V, the last letter in our alphabet is Z. The Greek alphabet does not have a Z, so their last letter is omega. Lowercase omega looks like italics W. And what we're going to see is that these are going to all tie together by the radius. So the linear velocity is going to be the radius times the angular velocity. And linear acceleration is going to be the radius times angular acceleration. We really don't use this one very much. This one we're going to use quite a bit. What about sines? So what do we do with sines? Because when you're doing linear, we had this, that this would be positive and that would be positive if you were using a standard coordinate system. So what do you do for angular? Well, the convention is that if you're going clockwise, that is going to be negative. And if you go counterclockwise, about an R in there, counterclockwise, this way, that's going to be positive. Now, I have seen AP switch this up, and it's really unfortunate because that's the only time I've seen anybody not use negative for clockwise and positive for counterclockwise. I have a mnemonic. The way that I remember this is if I am taking a timed test and the clock is running down, I'm running out of time, and that's a bad thing. So that's very negative to not have enough time. That's my mnemonic for remembering. What we need to talk about now are units, though, because I mentioned degrees and I mentioned revolutions, and that's not our standard unit for rotation. So let's talk a little bit about units. Okay, we had revolutions or turns. We have degrees. And hopefully you know that there's 360 degrees in a circle in one revolution. But the unit we really want to use is radians. This is the standard unit. And so everything has to get converted to radians when you're working on problems. Well, how many radians are in a circle? Did you say 2 pi? If you did, that would be correct. So one circle, one revolution has 2 pi radians. And in a lot of your math classes, you probably left this in terms of 2 pi, but in physics, for whatever reason, they estimate pi. So this is 3.14, so this is going to be 6.28. This is going to give us conversion factors of one revolution is 6.28 radians, and 360 degrees is 6.28 radians. So just like you did with converting, everything has to be in kilograms, everything has to be in meters. Whenever you work a problem, you have to convert into radians. You can't leave things in degrees, and you can't leave things in revolutions. So let's take a look at a couple sample problems that are going to incorporate these equations and conversions. Scroll down here. All right, what is the linear displacement of a wheel with a 0.1 meter radius after 1.5 revolutions? So linear displacement is x. And we want to know, we know that x is equal to the radius times theta. So we have this is 0.1, but I have 1.5 revolutions. So I have to convert this to radians. So using our good old dimensional analysis that you learned in chemistry, we know that one revolution is 6.28 radians. So that's going to be 9.42 radians. And when I multiply this together, I get 0.942 meters. All right, well, what about linear velocity? Now, one of the things that I'm going to be repeating is that everything in the angular world mirrors what happens in the linear world, in the rotational world and the linear world. So if we're looking at linear velocity, and we know that that's going to be x over t, delta x over delta t, then angular velocity is going to be delta theta over delta t. So instead of using x, we're going to use that. And what we want to do here is we're going to go from a rotational velocity to a linear velocity. So we also know that this is equal to radius times omega. So if I rewrite my equation, I can say that my straight line velocity is going to be equal to the radius to my displacement over time. The problem gives me this, but it gives me my displacement in revolutions. So I have to convert that. I have 2 revolutions, and I have 1 revolution is 6.28 radians. So when I multiply that, I'm going to have 12.56. And then I can just plug in my numbers and solve. So my radius here is 0.1. I have 12.56 radians, and my time is 0.97 seconds. And so when I solve for my linear velocity, I get a value of 1.29 meters per second. All right, that is, whoops, cut off my screen there. So what are our takeaways? Our takeaways are that the linear world and the rotational world are connected, and they're connected through radius. They're also connected by the fact that every value we have in the linear world, we also have in the rotational world. So we have Greek symbols for rotational. We have alphabet symbols for linear. Clockwise is negative, counterclockwise is positive usually, and you have to be able to get everything into radians. All right, that is all for this introductory video. We'll see you in the next one.